Okay.
There are the priors, but I generally call them the sparsity.
Share screen. Share. And play. If you're around. Okay.
If you have questions, maybe you can post them and we will try to answer it. You know, like this.
Pass is just. Stay here for. No. Oh.
Yes.
Okay. 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 Right. Okay. Can you hear me well? The other side? Okay, probably yes.
Probably yes.
Okay, so first, let me thank the organizers for putting this together. I'm quite happy to see like real faces here after a long time. I'm sure our friends across the pond have the same feeling. So it's quite good actually that I don't have to do a lot of intro. Johan covered some of the intro, so I'll try to be quick on that. Because here there are two kinds of papers that I want to speak about. And so let's see if it's speaking on time. So first, before starting, about the title, is a title that actually I borrowed from a blog post from Soledad Villar, where she was discussing in 2018 some of these new applications of generative models to regularize inverse problems. And I thought it was a very cool title. And she was asking, okay, are these generative models the new sparsity? And actually this talk aims at answering this question, at least in some toy models where we have control over everything like in the case that Florent was presenting. So these are my collaborators in these two works that I'm going to present today. Some friends from Paris and here EPFL. So just before starting with the actual problem, I just want to make sure the setup is clear for everyone. So here we are doing inference, or we're trying to solve an inverse problem. We have a signal. This signal has been generated from some distribution, has been sent to the statistician through some channel. And the statistician observes the corrupted version of the signal and wants to actually get back the signal that was generated. And actually, you're going to be always working in this talk on the base optimal setting, where actually the statistician knows everything about the process that has corrupted the signal and the distribution that has generated the signal. She just doesn't know the specific realization of the signal. So it's about recovering this specific realization. So it's a planted setting based optimal inference problem. And what are the questions we are interested in answering in this sort of problems is how many samples actually the statistician needs to actually recover the specific realization, actually how to do this in practice, or which kind of algorithm she can use actually to recover the signal. And given these two questions, what is the role of the structure or the prior distribution that the statistician has in the recovery? So different structures, you might imagine that might lead to different types of algorithms to reconstruction. So here are some of the archetypical examples of problems that fit this general framework that I just introduced. So we have denoising, matrix factorization, that's exactly what Florent was speaking about. And we have two other very celebrated problems like compressed sensing and its cousin, phase retrieval, where actually the signal is compressed by multiplying by a matrix, corrupted, and then in the phase retrieval, we also lose the information about the phase. Okay, so people have studied a lot these kind of problems in the past years, and a lot of the works have focused on the third question, on structure, in a simple model of sparse signals. So we know that many kind of class of signals admit sparse encoding in some basis. So we can think about sound in Fourier, we can think about images in wavelet basis, and therefore you would imagine in principle that, okay, since I know the distribution of the signal, the fact that there are many zeros on my signal, I have less information to recover. So it's going to be easy. But actually, because of the combinatorial problem of finding all the zeros, often sparsity reflects in some algorithmic difficulty, because actually it's very hard to find the exact configuration of the zeros. So not always we can leverage this advantage of sparse signals in terms of algorithms. So we, in this work, we wanted to ask the question in terms of how does the sparsity and all these works that have studied the sparsity in these problems that I have introduced, how do they compare to other kind of encodings? And specifically, this kind of a generative encoding, generative neural network encoding that people have been looking in practice since 2017. So in particular, we are thinking here about neural networks. So your signal actually being sampled from a trained neural network. And we know that, neural networks are able to do amazing things. For example, they are able to represent, to learn the distribution of realistic images from a latent representation that is just Gaussian noise. So at least in our mind, what we're trying to do is the following. Imagine that someone somewhere has trained in a huge data set with a lot of computational power, has trained a generative network to actually represent some class of signals that you are interested in, let's say images. So someone has a lot of computational power, has trained this neural network, has uploaded on GitHub. Then the statistician is going to get this neural network has been trained that presumably understands well what is an image and what is not an image. And we are trying to ask the question, can we use this knowledge that has been learned by the neural network to actually perform better inference or to regularize these inverse problems? So that's kind of the setting that we have in mind. So actually the signal has been generated from this neural network. The person who is performing inference knows that, has the weights of these neural networks. And we're trying to ask whether she can use these weights to actually infer better. Okay, so that's for the setting. And here I'm going to try to answer this question in a very simple model, which is the model that Florent was speaking about, actually a simple version, because here we don't have a tensor plus a matrix, we just have a matrix. So that's the matrix factorization problem. Actually, my signal is drawn from a distribution, can be a sparse one, or in the case that I'm going to be interested, these generative networks. Then you perform the tensor product of the signal with itself. So we produce a matrix. You add some Gaussian noise, additive Gaussian noise, and the statistician is observing this P by P matrix, which is the tensor or the matrix corrupted by some Gaussian noise. Okay, and the goal is going to be to reconstruct X star from the knowledge of the distribution of the signal, the noise level that I have introduced, and in particular, we're going to be interested in high dimensional limit, where the dimension is going to infinity. So it's very hard to sample from the posterior that you could, in principle, think as an algorithm, knowing the information of how the signal was corrupted. And the noise level is going to be of order constant. Okay, so what is known about this problem in the sparse case? So now we consider a very toy model for a sparse signal, where you have a mix between some Gaussian components and some zero. And here I have a density rho of non-zero components. So when rho is equals to 1, I have just n, just a Gaussian. When rho is equals to 0, I have just zeros. So this is a plot from a work by Thibault Lesieux and Lenk and Florent, where they have shown that for this problem, where AMP, the algorithm that Florent was speaking about, is the best known polynomial time algorithm for this problem, they have shown that actually there is exactly this phenomenon that I was describing before. There is exactly this problem that for certain sparsity levels, AMP is not able to reach the statistical optimal performance. So there is this hard phase. So this figure has a lot of information, but I'm just putting here pictorially what is going on. So here you have the performance, so the MSE of the algorithm compared to the MSE of the statistical optimal estimator, which is the Bayesian estimator for this problem, because we have all information about how the signal was generated and how it was corrupted. And we have this hard phase here that actually where AMP is getting stuck. So the question we want to ask is, okay, if now I change the distribution of the signal, and instead of having a sparse signal, I have a neural network of depth L. And here, that's important. We are going to focus on the case where the weights are random, Gaussian random matrices. So we are not considering the trained case, which would be, of course, what we would like to do. But so far, we only know how to do the analysis for the random case. The question is, given that the signal is sampled from this neural network, and given the knowledge of this distribution, can we actually make better, make better inference than in the sparse case? Okay, so this is exactly the same theorem that Florent showed to you, but in a more vanilla case, because again, we don't have the tensor. Actually, in this high dimensional limit, we managed to characterize exactly what is the MNIST for this problem. So the error achieved by the statistically optimal estimator for the problem. And actually, in the high dimensional limit, This is characterized by minimizing a certain function, this potential. This potential is given in terms of mutual information between the signal and a corrupted version. And actually, we are quite lucky because before us, some other people have computed this mutual information density. So when it exists, our theorem gives the performance of the Bayesian estimator, and some people have shown both rigorous and for 2 layers, but also have computed heuristically for more layers what is this mutual information is. So we can just read these works, plug in our formula, and characterize the performance of the Bayesian estimator for this kind of prior. And these are some curves of how it looks like, the performance of the Bayesian estimator. And here we cover some expected behavior that, for example, for different architectures, increasing the depth of these networks, like it's easier and easier to recover the signal because you're having more information. But of course, the question we are really interested here is not the performance of the Bayesian estimator, but how does an algorithm compare with that? Like, so can I find an algorithm that actually can leverage this advantage in terms of actually computational power? Okay, so as AMP is the best algorithm we know for the sparse case, actually we are also going to look into AMP in this case. And actually AMP has this very nice property that it's very easy to compose it. So once you have one block of AMP, so let's say once you have one layer of AMP here for the spiked problem, and you have another block of AMP for the generalized linear estimation. So here I'm just considering one layer of generative prior. It's actually very easy to go and compose it together and have an AMP for the composed system. As long as we are base optimizing what we're doing, it's very easy to write down this algorithm for the composed system. And actually, you can iterate this as much as you want. You want to put another layer, you put another layer, and so on. And there is a very well-defined prescription to do that. So it's a very friendly algorithm for this reason. So here is how the algorithm looks like for one layer generative prior. So yeah, if you know AMP, like this is gonna ring a bell. If you don't, it's like kind of a beast. So my goal is not to describe how this works, but it's just an algorithm, iterative algorithm, which is first order. So just multiplying by matrices and then applying some scalar functions, and it produces an estimate of the marginals of the posterior distribution. So that's all you need to know. About AMP if you haven't seen it before. And actually, you don't even need to code it because some very good people have actually implemented a package where actually you can just like you do in PyTorch, you do like import, and then you add one layer, and then you add another layer. As long as you are composing a tree of different AMPs, the package can handle it. So, and also if you have an inference problem which you are interested, and you know how to write AMP for this inference problem, for this likelihood, then you can just go there and put there and compose with the ones that are already implemented. So it's a very compositional friendly algorithm, and this package implements it. So you don't even need to code it. And so now the question is, given that you have an algorithm and given that you have the statistical optimal performance, how do they compare? Is there a gap just like for the sparse case? And for our surprise, actually, for this problem, there is no gap. Actually, AMP is able to achieve the statistical optimal performance for many of the natural generative architectures you can think. So just choose your favorite activation function like ReLU, compose many ReLU together in a multi-layer structure, and actually compute the Bayesian optimal performance and run AMP, and you're going to see that they agree. So AMP is able to leverage all this knowledge of the prior to achieve the optimal performance. So there is no statistical algorithm gap in this problem. So this analysis is in the asymptotic limit, but also there has been follow-up works to ours who have shown that this conclusion holds true also in the non-asymptotic one. And I think probably Paul Hand maybe might speak about that, I think on Friday, I don't know, today later on in Berkeley. So yeah, if you're interested, he's going to probably present about that after. Okay, another cool thing about AMP is that it not only provides like this algorithm that we can achieve the optimal performance, but it's very easy from AMP to get a spectral method that is just comparable to like PCA. So in this problem, if you didn't know anything about the information about the prior, the natural thing you would do is just you take your matrix, you take your spike matrix, you take the leading eigenvector and use this as an estimate of your signal. And if the prior is Gaussian, then this is a very good thing to do. But if your prior is like a generative network or sparse, actually you're not leveraging the knowledge of the prior you have, and PCA is not going to do very well in this task. However, we were able to get our AMP, linearize it. We obtain a spectral method that comes from it, which we call the LAMP or lump, linear AMP, which does a very similar thing to PCA. So it takes the leading eigenvector of one matrix, but not the spike matrix. Now it is a modified matrix that actually depends on the population covariance of the distribution of the signal that you're trying to estimate, of the spike. And actually for a single layer, we can actually compute what this population matrix is, depends on the weights of the generative network. But it's quite cute because it gives a very out-of-the-box way of estimating your signal, taking into account the structure that is encoded into this matrix K, the population covariance. Okay, and if you plot the performance of this algorithm against PCA and against the optimal Bayesian estimator, it's quite good because you can see here that lump, which is the green dots, actually correlate with the signal at the same threshold, noise threshold as AMP. So of course, the performance is worse because the linearized version of AMP, but it correlates with the signal at the same threshold. So it's quite good. And in particular, it beats PCA, which starts correlating with the signal always at 1. So we can also improve over PCA using this linearized version of AMP, which is easy to code and to run. And actually, an idea that we had is even like, okay, let's give a try this algorithm and try in a distribution of signals that we don't even know where they come from. Let's try like some real images and estimate this covariance matrix just by the empirical covariance of the signal over the data set that we have. And you can see that even in this test, like the linearized version of AMP is able to correlate with the true signal at a noise level, which is much higher than PCA. So that's kind of a cool application. Okay, so that was about it for the spiked matrix model. And what I want to do in the last 7 minutes that I have is to talk to you about another problem. So of course, when we had this conclusion that we were like quite surprised that actually generative priors for the spiked matrix factorization problem didn't have this computational to statistical gap. We said, okay, we need to try harder problems that have bigger, notably bigger gaps. So we went for 2 problems, which is phase retrieval and compressed sensing. And in particular, phase retrieval is a problem that we know that has a particularly big gap. I'm going to show to you. So just before to recap again what these models are, like both of them can be written down as a generalized linear estimation problem. You have a signal drawn from a distribution, you apply a matrix, usually a compressing, then you apply a nonlinear activation component-wise. This can be the modulus for the phase retrieval, or can be whatever you want, but okay, for the compressed sensing, it's just a linear function. And then the statistician is observing the result of that. And you can also add noise on this process. So here I wrote the noiseless version, but of course you can add another additive Gaussian noise. Okay, and the goal is the same. We want to reconstruct the signal, given the distribution, given the sensing matrix A, activation function sigma, and actually here phi. And we want to do this in the high dimensional limit where the number of samples and the dimension go to infinity, while the ratio is kept of order 1. Okay, so this is the phase diagram from work by Jean Barbier, Lenka, Florent, etc. that characterize the phase diagram for the sparse version of phase retrieval. And what I want you to pay attention in this phase diagram is that even when rho goes to 0, which means that you have a very, very sparse signal. And remember, the statistician knows that. So she knows that there are almost all the signal is zero. Even in this case, you still have a statistical to computational gap with respect to AMP. And just a comment about this region, which will not be interested for us in this talk, but recently has been some work by some colleagues that are showing that actually in this point, where actually just have a Gaussian signal, this gap, they built a phenomenal time algorithm that actually can achieve a better performance than AMP, which is quite cool. But okay, that's for another time. Now we want to focus more on the sparse region of the space diagram. Okay, so here we can do the same analysis that we did before. We can compute the statistical performance. So we can compute the performance of the base optimal estimator. We can build an AMP for this problem. And this AMP, we can put as many layers as we want, just like we did for the spike case. And then we can just plot what AMP, how's AMP performing in comparison to the statistical optimal performance. And okay, so the conclusion here is that even in the generative case, we are observing these hard phases. So remember, these are phases in which AMP is not correlating to the signal, but statistically you have enough information to recover the signal. So actually there is these gaps. Here we see that as you increase the depth of your generative network, this gap is getting smaller and smaller. And actually, we can plot a phase diagram just like we had for the sparse case. And here I'm leaving this line here for comparison is the line of the sparse case. As you remember, even when rho goes to 0, we had this gap between the performance of AMP and the Bayesian estimator. And in green, red, and yellow, I'm plotting respect to the generative prior. So green means that the problem is easy. So actually AMP is able to recover the signal exactly. So yellow is a hard phase. It's exactly when AMP fails, but you have enough information statistically to recover your signal. And red is the impossible region. Is that like statistically, even if you had exponential time, you wouldn't be able to recover, to correlate with your signal. So as you can see, the generative priors for this model is able to outperform the case where you match the compression rate of your prior with the sparsity level of the sparse prior, and in particular the hard phase, which is what is interesting us and what is the topic of this workshop. It's much smaller, and this is for one layer generative prior, but we can iterate this for more layers, and this hard phase asymptotically disappears. So it doesn't disappear for a finite number of layers, but you get a very small hard phase. And that's for the phase retrieval. More or less the same conclusion holds for the compressed sensing. I didn't put the phase diagram here, but for the compressed sensing, which is an easier problem, the hard phase is smaller, and also for the generative prior is smaller than in the sparse case. Okay. So as I was saying, generative priors have a smaller algorithm gap, and that actually goes into the direction of another work by Pohan's group, which built an algorithm suggesting this as well. It's not AMP, but it goes in the same direction. Okay, to conclude, I have argued that generative priors have comparatively smaller algorithmic gaps than their sparse counterparts, at least in this set of archetypical random toy models for inference problems. And I have shown that algorithmic gap can be reduced with both depth and also with the compression of the signal. So really, going back to Soledad's question, I want just to leave a provocation. Actually, are generative priors the new sparsity, or are they better than sparsity? So in this context, we can say that they seem to be, at least algorithmically, more advantageous than sparsity. And of course, this question doesn't say anything about a real-life application. So that I leave for our engineering friends to actually go back to this question in actually applied problems. Okay, with that, I would like to thank you for the attention. And these are the archive links for the 2 papers that I have covered here. Thanks.
It could be in a room with the actual apples.
Yes.
Bruno. Are there questions for Bruno, either here or on Zoom or in person?
I have one. If all others are coming. So, what if you didn't have the nonlinearities? It feels to me that what's happening is the top of the spectrum of all the matrix of the weights is giving a certain bias for you to be, the covariance is going to have a high eigenvalue there.
Mhm.
And so if you had random orthogonal matrices instead of Gaussian matrices, this shouldn't happen. And then the prior maybe doesn't say anything. So is the problem a lot harder if you have, like if you replace with orthogonal matrices instead of Gaussian matrices, say? Like, do you see a difference, or do you have any intuition?
Oh, I mean, we didn't try that, but I think it can be done with the orthogonal matrices. I mean, we definitely can do orthogonal matrix for one block. And the argument here is that all these methods, both from the AMP or for the computation of the base optimal estimator, what we have learned in the past few years is that it's quite easy to compose them. That's what I showed in this compositional principle. So I'm pretty sure we can do for the orthogonal matrices as well. And
random orthogonal.
Random orthogonal.
Yeah, we did that in the paper with Mario. Was actually that case.
Okay. For the that is true. So yeah, actually, this has been done for the case where we have the composition of many GLMs. And what was the conclusion?
That you can do it.
You can do it, but in terms of
but you actually, does the prior tell you anything? Because there's two things in the prior. There's the real and there's the fact that it's pushing you towards the directions of high eigenvalues of W.
We didn't analyze the phase transitions for that case. It's just that it can be done like the method, but we didn't analyze the phase transitions.
But it's a very good question. I think it probably you should look at, because if the formula is there.
Because if you take away the real lose, all you're doing is you're biasing for certain directions, and then it makes sense that the linearization is the covariance.
Mm-hmm. Mm-hmm. For the spectral method, you say in the spiked version. Yeah. I mean, we don't have the spiked version for that with the orthogonal matrices, but I mean, as I said, the theorem holds this mutual information. We have the mutual information, so it's just a question of plugging and checking.
Maybe we have questions from Berkeley or.
So we had a break scheduled, but since we're behind schedule, do you want to move ahead with the next speaker? Is that good with you guys in Europe?
It's up to you.
For us, it's fine.
Yeah, for us, it's fine.
Great. So we're very excited to have Guy Bresler here telling us about reductions.
Great. No need to clap, at least not yet. Yeah, if it goes all right, you can consider clapping at the end. Yeah, so it's just wonderful to be here presenting at this workshop. Really enjoyed hearing people's new work and ideas and things. So I'm going to tell you about reductions, as Alex said, and the primary aim of this talk is to maybe try to demystify a little bit of some of these ideas, to take some of the magic out of these ideas if they've seemed sort of unapproachable. And maybe the reason for this is because there's this sort of folklore in complexity theory that average case reductions in particular are really challenging. And so we learned this sort of from the beginning, and I remember taking complexity courses and being told, like, all right, average case reductions, you don't want to go there. I mean, there's been this Levin stuff that's really nice, but we haven't made a whole lot of progress since then. And so the primary maybe aim of this talk is to convince you that we should be optimistic about this direction in general. All right. So yeah, with that said, it'll be a little bit tutorial in nature. So feel free to interrupt with some quick question. I might have forgotten to explain something, some notation, whatever. Don't hesitate to just ask. All right, so this is joint work with Matt Brennan. And as many of you know, Matt suddenly passed away earlier this year.